you forget to open the microphone, right? Actually, yeah, this one is Shure MV. Oh, you forget to turn on also the microphone here. In this one, okay, works fine. Oh, we forget all the time the microphone. Yes. Oh, okay. Yes, poor. Now we have to stop. We have to stop the video here. Wait. We have to stop the microphone, the video to. Okay. It's the no. Papa with. Okay. The video bitrate is somehow so you could use this. Permit to shot win. With green shot win. Go ฝั่งนี้ก็สิดิสิดิใครไม่รู้ so that's this is the let's take a look at this. Okay, the button series. All right. Okay. It's CO4. Try teach this CO4 today. It's in the first in this one here, but we're gonna have this see it. Yes, see it. Super see. Okay. Three places and yes, we forgot to turn on the microphone. The bit rate to be high times. Yes. Well, not to open the steam. Right here. Yeah. And the Safari, right? Safari is this one. I'm gonna move it to move to that's now we have to switch account to this one. Right. And let's see what's going on in your channel. And this one, right? Let's see this one to look at the white version of the to look at the live version of the Streamlab. Right, yeah, and go to live version of Streamlab 2 in no, go to this account. But my we go to the Streamlab version. I'm going to Zoom version, right? The Zoom has no sound. Yeah, Streamlab. No, it's not made for G. Okay. It's not made for G. And just what is that? Zoom version. Right. Okay. But my okay. Excellent. okay. Anyone is watching? Okay. From 605, you have already right. We have now Thanagon, right? Thanagon at the OBS number 1 to OBS number 1 and สุภวิทย์นะครับพระสิทธิ์นะครับเหล่าศรีเมืองครับ and nothing more, right? No one more. Yes, one thing นนทกรด้วยนะครับนนทกร okay, one thing I need to inform you is the following นะครับมีบางสิ่งที่ผมจะต้องเรียนแจ้งคุณก่อนนะครับสิ่งที่จะต้องเรียนแจ้งคุณก่อนก็ดังต่อไปนี้นะครับright that here okay นะครับก็ขอเรียนแจ้ง M605 นะครับ605นะครับก็คือว่าวันศุกร์ที่จะถึงนี้เนี่ย28วันนี้26นะครับเพื่อนมาถึงแล้วหรือยังนะปนทัศน์นะครับปนทัศน์ด้วยนะครับที่ OBS นะครับทุกคนโอ้โหขอเก็บชื่อชัยสิทธิ์ห้อง604ก่อนนะส่งให้เขาก่อนโอเค604 right M604 where is that here ส่งเดี๋ยวลืมนะครับโอเคก็เรียนแจ้งคุณก่อนนะครับสำหรับห้อง605นะมีปานทัศน์พิมพ์มานะครับก็ไม่รู้มาครบกันหรือยังนะครับวชิรวิทย์ก็พิมพ์มาแล้วด้วยนะครับคือนะครับต้องเรียนแจ้งคุณว่าวันศุกร์ที่28นะครับก็เราจะไม่ได้พบกันนะไม่ได้พบกันหมายถึงว่าผมไม่รับผิดชอบนะครับหมายถึงว่าคุณครูหรือท่านอาจารย์ณัฐพงศ์ครับที่สอนน่าจะเป็นวิชาเลขคุณนะครับเขาจะขอคืนนะครับก็คาบที่3คาบที่4ตอนรู้สึกจะเป็น10ถึง11:50เนาะของคุณนะครับเขาจะขอคืนนะครับดังนั้นเราจะไม่ได้พบกันนะครับทุกคนรับทราบนะครับโอเคไหม605นะครับโปรดรับทราบนะว่าเราจะไม่ได้พบกันวันศุกร์นะครับดังนั้นวันนี้เราจะเรียน2คาบแล้วก็น่าจะวลินทรด้วยนะครับน่าจะสั่งกันบ้านเลยนะครับแล้วก็ไม่สั่งดิเพราะว่า604เขาจะต้องอีกครั้งหนึ่งเนาะคุณไม่ต้องมีกันบ้านในทิศนี้เนาะแล้วก็604เขาจะเริ่มคาบนู้นเลยนะครับคาบที่2เลยนะครับคือผมจะสอนแค่เฉพาะคาบแรกของวันศุกร์นี้เท่านั้นโอเคก็นั่นคือ28นะครับครั้งแรกนะที่มีการเปลี่ยนแปลงครั้งที่2ก็จะเป็นตรงนี้นะครับ605คาบ4นะครับหมายความว่าคาบที่2ของเราอาทิตย์หน้าวันศุกร์หน้านะก็ผมก็จะสอนแค่คาบเดียวแล้วก็อาจารย์ณัฐพงศ์เขาก็จะขอคืนนะครับโอเคไหมวลินทร์ พวัตรรับทราบไปด้วยนะครับบอกเพื่อนนะตามนี้นะครับอัดวิดีโอไว้ให้แล้วนะคุณก็รับทราบกันไปนะครับ what else nothing more right ก็จะประมาณนี้หากมีข้อสงสัยใดนะครับให้ท้วงติงกันได้ครับว่าผมทำผิดทำถูกสิ่งใดนะครับโอเคก็จะประมาณนี้นะครับโอเคlet's get back to our this is the M604 right we're gonna open a new file Proton this one it's gonna be called what is this okay copy this this one M605 okay this one and open also here for you M605 M604/M605 this one okay you have reached so many topics before I hit M604 because you don't have any trouble in electronic setting or online classroom setting. The M604 suffers a lot from the missing time during setting. Okay, M605. Why should I? Oh, okay. I have to go to your classroom. Right? 6. Oh no, the same file. 60526. This one. Okay, in yeah, to go. Yes. If I can remember, we would arrive at this one, right? The power plant. Let me check it again in the classroom. นะครับห้อง605นะครับผมแจ้งไปแล้วว่าวันศุกร์นะครับเราจะไม่ได้พบกันนะเนื่องจากว่าอาจารย์ณัฐพงศ์เขาขอชดเชยนะครับผมไม่ได้เรียกร้องอะไรนะเขาพร้อมกลับมาคืนนะครับก็ผมก็ให้เขาคืนทันทีเพราะว่าแค่ช่วยเหลือการในยามที่เขาบาดเจ็บแค่นั้นเองนะเขารักษาตัวยังไม่พร้อมอะไรอย่างเงี้ย Okay, let me check where did we arrive last time เรา nuclear reaction โอเคไหมครับเรา nuclear reaction โอ้คุณก็จะนำ604แค่นิดเดียวสิเนาะ right เราก็นำคุณก็จะนำ604แค่นิดเดียวyes รูปนี้หลังรูปนี้ครับโอเคนี่คือของเก่าของเราครับโอเคso good afternoon everybody, welcome you to SCI33206, which is the last person in OBSNo2 channel, right? And for the people in Streamlab, you are Proton, right? Number 2, no one in Zoom 2 channel, right? Okay. หาเอาเองนะครับมี4ช่องนะครับผมบอดคาสต์ไลฟ์อยู่ตอนนี้4ช่องครับใน YouTube นะครับคุณหาเอาเองนะครับกดคำว่า SCI นะครับ33206แล้วก็วันนี้ January 26 นะครับจะมีอยู่4 channel นะครับใน YouTube นะครับเลือกเอาอันไหนนะครับที่สัญญาณดีเพราะว่า604ที่ผ่านมาผมลืมเปิดไมโครโฟนอ่ะก็อยู่กันได้ก็ไม่แจ้งนะว่าใน Zoom ก็ลืมแชร์หน้าจอนะครับก็ไม่แจ้งกันโอเค anyway ดีเนี่ยพยายามเปิดเครื่องหลายๆเครื่องเพื่อว่าเช็คสัญญาณนะว่ามันออกดีไม่ดีนะครับมันก็ลืมจนได้นะโอเค Okay, fission reactions are always exergic. Okay, it means the mass difference is positive, right? And because the fission fragments have greater binding energy, you know, the unstable nuclei that has not so good energy binding per nucleons turns to be a smaller nuclei, turn to be two smaller nuclei, daughter nuclei, let's say, and in those smaller nuclei, they have better binding energy per nucleon, so they are more stable than the initial nucleus like uranium-235 and so on, right? So the fission fragment have greater binding energy per nucleon than the original nucleus for that reason. And the total kinetic energy of the fission fragment is enormous, so it means it's very big. The outcome energy, okay, you know, for producing electricity or for making the nuclear weapon, nuclear bomb and so on. Yeah, the people use this nature, the high energy caused by nuclear reaction process, and it's around 200 mega electron volt Okay, and yeah, it's very, very dense energy. You know, the densest form of energy is hidden in terms of mass, okay, not in fossil, not in electricity, it's in terms of mass. And yeah, the amount of energy released by the fission of a single heavy radioactive atom is around 100 million times the energy caused by the combustion of one molecule in the gasoline engine. Okay, you know, we use gasoline engine for driving the car, right? And yeah, fossil seems to be a very, very dense piece of energy, right? But the mass is more dense than that. Okay, in what you could see is the energy by the friction process is 100 million. Okay, I don't know, 10 to 8 times higher than the amount of energy by fossil in the internal combustion engine car. Okay, yeah, you could see the scale, the more sophisticated, the higher level of energy packaged by the fission energy process. And now it's time for us in physics to compute something, right? Yes. If the disintegration energy Q per event is 208, okay, it's almost the same as 200 as said in this sentence, 208, right? It's quite close to this one. It depends on which process and some other factors, okay, and yeah. It's taken from book number 1, example 30.1. Okay, if the disintegrated energy Q is 208 mega electron volt per process, okay, per decay, and per reaction, you can see. Calculate the total energy released by uranium 235. Let's say the isotope 235 uranium of 1 kilogram, okay, of 1 kilogram, and what is the total amount of energy released by uranium 235? This one, okay. So how could we determine the total energy? So we have to find the number of nucleon, or the number of atoms of uranium by 1 kilogram. Okay, you need to know the number of atoms, which is equivalent to the number of nuclei, okay, by 1 kilogram of uranium, and then you multiply that mass with 931. Oh no, by this one, by you multiply the number of nuclei by this number, because this is the disintegration energy per nuclei per reaction, right? Yeah. So let's do that. The number of uranium 235 nuclei per 1 kilogram could be found from you know, 235 is the mass number, right? It's 235 gram per mole, right? So in order to do that, we know that the number of particles per 1 mole is denoted by the Avogadro number, right? Which is Na, and it's equal to 6.022 times 10 to 23 nuclei per mole, or atom per mole, okay, for the chemistry. But for us in nuclear physics, we would say nuclei per mole, okay, which is equivalent to atom per mole in chemistry. And for us, we need to convert 135 gram to the kilogram, right? It's SI version. As we know, 1,000 gram is equivalent to 1 kilogram, right? So we need to divide this number by 1,000. So it's going to be 0.235 kilogram per mole. And yeah, that's the number of nuclei per mole. So we have right now the number of nuclei per kilogram, right? So we got the fraction after you leave here 6.0 through 210 to 23, and you make the division of these two numbers, you get 2.5626 10 to 24 nuclei per kilogram. Okay, so this is the number of nuclei by uranium-235 per 1 kilogram. Okay, yeah, we have already got this. Okay, next one is that we're gonna convert the number of nuclei in 1 kilogram for uranium-235 to be energy. Okay, by multiplying this number with this amount of energy, megaelectron volt per reaction or per nuclei. So 208 megaelectron volt per nuclei times this number nuclei per kilogram. We're gonna get the energy. Okay, just make the multiplication, simple multiplication. We get 5.3301 10 to 26 megaelectron volt per kilogram. Okay, it's the total energy caused by 1 kilogram of the uranium-235 isotope. Okay, and the next question is that how many kilogram of uranium-235 would be needed to satisfy the world's annual energy consumption? For, let's say, this is the amount of energy that the people around the world will consume per year. Okay, in 1 year, let's say if the number of population stay constant, but actually it's not the case because we use more and more energy every year, right? So if this amount is constant, remains constant for every year, so what is the total amount of uranium we need to supply this energy consumption, energy need, which is 4 times 10 to 20 joule. Okay, that's the SI unit, right, for the energy. But for us in nuclear physics, we compute the energy, we observe the energy in terms of megaelectron volt, which is the SI version divided by the electron charge value, right? Okay, this is the amount of energy we could get from 1 kilogram of 1 kilogram of uranium-235. We're gonna compare it to the energy that is required by human around the world, okay, all over the world. So number of kilogram that we need will be the ratio between the desired amount of energy around the world by the amount of energy we could get from 1 kilogram of uranium. Okay, whether in terms of joule or megaelectron volt, we're gonna convert it later. Okay, yes, 200 4 times 10 to 20 joule as the numerator, nothing more, right? And we wanna convert megaelectron volt to be joule, okay, so that the joule can cancel each other at the numerator and at the denominator, right? So we will convert this one, and what we could do is what is the amount of joule per megaelectron volt? Yeah, 1 joule per electron volt is 1.6 times 10 to negative 19, right? But once we observe it per megaelectron volt, we're gonna multiply it by 1 million, right? 10 to 6, right? So 10 raised to 6, so 10 to negative 19 multiplied 10 to 6, which is million, is going to be 10 to negative 13 only here, okay? And after that, you make the multiplication and you make the division here, and it turns out that the number of kilogram of the number of uranium in kilogram will be 4.6845. million kilogram. Okay, and that's the amount of uranium we need to supply the energy for the people around the world without any other energy sources. Okay ปิดทัศน์มานะครับที่ธนทรนะครับก็กดชมวัดนะครับก็บอก605นิดนึงครับว่าวันศุกร์นี้นะครับเขาจะชดเชยนะเราไม่ได้พบกันนะครับแล้วก็วันนี้ก็คงไม่สั่งการบ้านด้วยนะครับเพราะว่าต้องให้604เขากระดึบขึ้นมานะครับจำนวนการบ้านเท่ากับคุณครับ alright yes that's the number of kilogram right it's mega kilogram okay we I don't know 1 ton 1000 ton 4.7 4,684.5 ton per year. Okay, that's the amount of uranium we need to supply the total energy required on Earth. Okay, around the world. Now let's move to the next example. Next example, we talk about fission again. Okay, in the same way, it's a fission by uranium, maybe uranium-235, the same thing. Okay, let's say if the fission process or the nuclear fission reaction would give you 200 mega electron volt per process per reaction. Okay, once you decompose one nucleus of uranium-235, you will get the energy around 200 mega electron volts. And how much uranium has to undergo fission per unit time to provide 3000 megawatt of thermal power. So this is again the amount of energy. It's not energy, it's power, right? Because watt means joule per second. It's the unit of the power. It's not energy, but it's energy per time, right? So this one is equivalent to 3,000 million is 3 times 10 to 9, right? 3 times 10 to 9 joule per second is watt, right? And yeah, let's say each process would give you 200 mega electron volts. Okay, we're gonna convert this one to SI and we make cancellation. We can get the number of we can get the amount of uranium. Okay, now from 89, the number of nuclei for uranium-235 per kilogram is this one, this number, right? 2562, right? 25626 and 10 to 24. Okay, very large amount. That's the number of nuclei we could get from 1 kilogram. And yes, the number or the amount of uranium in terms of kilogram per second will be the required power, the power required by somewhere, right? By some places. 3 times 10 to 9, okay, 3,000 megawatt. So it's equivalent to 3 times 10 to 9 joule per second. Okay, that's the decided amount of energy, or no, power. And after that, we use the number of uranium-235 nuclei per kilogram times the amount of released energy. The amount of released energy from the fission process. Okay, and they say instead of 208, okay, they say 200 exactly. So we're gonna use N, right, which is the number of nuclei per 1 kilogram. Okay, it's 2.5626 10 to 24, and Q is the mega electron volt, the energy per nuclei, right? So yeah, you will get the amount of nuclei per kilogram. You get the energy release per nuclei, and after that you make the multiplication of these two numbers, and you divide to the desired amount of power by this product, and you get 3.6539 10 to negative 5 kilogram per second. Okay, you please note that megaelectron volt will cancel each other and joule will cancel each other here, so we move kilogram above and second will stay behind underneath, so we get kilogram per second as a unit for this quantity, which is the desired variable here, number of kilogram per second. We need 3.6 10 to negative 5. It's not easily understandable, right? 10 to negative 5 kilograms. So we convert this one to okay, this 10 to 3, right? So it's negative 2. Negative 2 means if we go further, we're gonna have 36, right? 36.5939 milligram per second. So in order to supply the power of 3000 megawatt, we have to burn or to decompose the uranium-235 isotope by 36.539 milligram per second. Okay, it's the amount of burning uranium per second. Okay, it's not the exact amount of uranium only. Okay, it's rate of burning, or let the uranium be in the fission process per time. All right, that's the nuclear fission. Okay, there are two examples to compute regarding the energy requirement, and before that we have calculated the reaction energy, right? The mass difference times 931.5 mega electron volt per atomic mass unit. Okay, now we finished already nuclear reaction. We finished the nuclear fission, and we are going to start the nuclear fusion here, this section. Okay, this topic. Okay, fission is the process of decomposing big nuclei to smaller nuclei, right? Okay, now let's talk about the opposite way. Okay, before that, the big nuclei is decomposed into smaller two daughter nuclei, right? Into two smaller daughter nuclei. And here it's in the opposite way. Nuclear fusion, okay, and this one is actually more powerful than the nuclear fission. Nuclear fusion is another reaction process. It's in the opposite way to nuclear fission. Okay, nuclear fusion means we combine two smaller nucleus, two or more smaller nuclei to be one bigger nucleus, or even more. Okay, not only one, not only a single nucleus, maybe two nuclei. Okay, in a nuclear fusion reaction, two or more small light nuclei combine to form a large nucleus. Okay, that's the general form of nuclear fission. We will go into the detail later. When two or more light nucleus combine to form a heavier nucleus, the process is called nuclear fusion, which is the topic here. Okay, we combine two light nuclei into a heavier nucleus. Okay, and after the process, we got also the energy, and this type of process is called fusion. Okay, nuclear fusion. It means the process that fuses some nuclei. Okay, nuclear. Usually the mass of the final nucleus is less than the sum of the masses of the original nucleus. So this is a good thing because the mass difference will be the mass difference will be connect the mass difference will be transformed into energy. Oh, what's the problem? There is internet connection to this channel. Yeah, we got that. Okay. Oh, internet works. Okay. Okay นะครับปล่อยอินเทอร์เน็ตเสียอยู่ตั้งนานนะครับผมก็ลืมเช็คตรงนี้ไปนะครับ Streamlab ก่อนอยู่นะครับ Streamlab ก่อนอยู่พิรทัศน์อยู่ไม่รู้ว่าดูกันได้หรือเปล่านะครับ anyway let's check whether let's check the stream here of the Streamlab แล้วพี่พลไปที่ Streamlab excellent อยู่นะก็อินเทอร์เน็ตน่าจะวิ่งดีอยู่นะครับก็ไม่มีใครท้วงติงอะไรมาผมก็ต้องสังเกตเอาเองครับว่าแต่ที่ขึ้น watch เนี่ยก็คือไม่ค่อยมีคนดูเท่าไหร่นะมีคนดูคน2คนหรือตัวผมเองผมก็ไม่รู้นะว่าใครเป็นคนที่ดูนะโอเคyes let's go ahead with that usually the mass of the final nucleus is less than the sum of the masses of the original nucleus. It means that let me write down something. This is the mass of the reactants, right? Mass of two things. Okay, and you get a bigger nucleus at the output. Usually the mass here is less than the mass less than the sum of the masses of the original nuclei. So the mass difference will be positive, right? Because the summation of this one is greater than this one. And the mass difference will be converted to the energy according to the Albert Einstein EMC squared formula, right? Yes, we go ahead. The most prominent nuclear fusion reaction is the one that take place in the sun and other stars like the sun. 3 examples of the energy liberating fusion reaction are in the following sequence. Okay, this is the sequential reaction process. Okay, it's a set of reaction processes. Okay, not only a single process like in the nuclear fission, right? In nuclear fission, you just decomposed. Okay, it's a series actually. You just decompose uranium, okay, to be smaller nucleus, and the output, which is neutron, right? Which are neutrons. The neutron will decompose another uranium or other material, so that the whole nuclear fission will take place automatically or continuously. But nuclear fission is different. It's a series of reaction process, not only a single decomposition like uranium 235 to become barium and krypton. Okay, nuclear fission is a little bit more complicated because it contains a series, not only a single fusion reaction, okay, but 3 or 4 reactions that took place together. Okay, and the process like here in the sun, okay, is not the one that took place in fusion. There are many more types of nuclear fusion reactions, but due to the time limit, okay, for us in the high school level, we will not consider all of that. Okay, you have to you have to go to the bachelor degree, okay, and study physics, okay. You will see more or complete process about nuclear fusion. Okay, the first process in the energy liberating fusion, like in the sun, is the following. Two protons. When the proton is denoted by 11p, right? P11 and H11 on the left. Two protons combine to form a deuteron. Okay, deuteron here, and a positron. And positron, right? It's similar to electron. It has the same mass, same spin number, but the charge is different. And positron is not easily stable, right? Usually it's gonna combine with electron to make the gamma ray or the photon and so on, right? We cannot find positron easily. So two protons combine to form, okay, the proton combine together to get deuteron, okay, a bigger version of hydrogen or the proton, right? Which is the bigger isotope of the hydrogen, right? Deuteron, D21. And another product is the positron, right? We get positron from this process too. In of course the electron neutrino. It's like it looks like a beta plus decay. Okay, you start the hydrogen, okay, the proton with another hydrogen, okay, and you get deuteron, okay, which is a bigger isotope of hydrogen. Yes, it's time to observe the reaction energy, right? Yeah, but most of them say fusion process would have less mass at the output, okay, as the output. Okay, this is these two things, the hydrogen's nuclei are the input. So we need to compute the mass of these two nuclei. So it's 2 times the mass of hydrogen 1, right? It's proton, but you should not use the mass of the proton, okay? This is actually the mass of complete hydrogen, okay, together with electron, because the mass without electron would be only the mass of proton. Okay, yeah, 2 times the mass of hydrogen, right? 2 times the mass of the hydrogen, because we have 2 pieces of hydrogen here, and reduced or subtracted by the deuteron, the mass of the deuteron 2,1, and the proton 0,1. Okay, proton has no nucleon. Proton is 1 charge equal to the proton, so it's 0,1. Okay, yes, what else? Yes, the mass difference, okay, and the next one is the mass of the deuteron, right? Just go to the table like this. Okay, you just go to the table. What is deuteron? Okay, mass of deuteron is 0.014101, which is this one, okay, and subtraction. And the mass of the proton, right? Mass of proton is equal to the mass of electron. Okay, don't worry about it. Mass of electron, where is that? Here. Mass of electron is 0.000548. Okay, simply speaking, 549. Okay, you make subtraction of these 3 quantities and you multiply it with 931.5 megaelectron volt per atomic mass unit. You get the total amount of energy, which is less than 1 megaelectron volt. It's 0.9315 megaelectron volt. Okay, that's the first process. But it's not the ending story, because once you get positron, this one, this particle is really unstable, okay, they are really active to other particle because it has positive charge, right? Yes, the proton will annihilate. The proton will combine with an electron in the environment, okay, around there. Wherever, whoever has electron, okay, proton will combine with that electron to form two gamma rays like this, okay. Proton plus electron is going to be deuteron plus proton, and of course we add the electron, right? And here is electron neutrino. The proton and the electron will combine themselves to form two gamma, okay, gamma rays or photon, right? Gamma is a kind of photon. And if you want to consider the energy from this process, you just find the mass difference between the input side and the output side. Okay, and what is the input then? Input on in equation 95 is two pieces of proton and one piece of electron, right? So we're going to use this one as the initial on the left hand side, which is positive, right? Two masses of proton or hydrogen 1 plus the mass of electron, okay? So one piece of hydrogen 1, okay, one piece of hydrogen 1 is 1.00825, this one, and two pieces mean we have to multiply by 2. And next is the mass of the electron, right? Mass of electron is provided here, which is a very tiny amount, okay, 0.00548, okay, it's 0.00549 approximately, okay, and subtracted by the mass of the deuteron, okay, deuteron on the right hand side. We don't take into account mass of photon and the mass of electron neutrino, or the electron neutrino, because electron neutrino has the mass even much smaller, 1 by 10,000, okay, mass of electron, okay, it's even less than that. So we don't take into account the mass of photon and electron neutrino because the value is not known right now. We just make the subtract to mass of deuteron, and we go to the table to pick up the mass of the deuteron. Deuteron means 1 proton, 1 neutron, right? Deuteron is here, so it's 2.014101, which is this number, okay. Then you make the summation and subtraction, you multiply it again by 931.5 megaelectron per atomic mass unit. And after that, you will get the outcome as the plain number, which is 1.9543. Okay, this energy will be allocated to maybe to neutrino, to photon, and so on. Okay, our proton, the second process in this series is that once you get deuteron as the output in the previous process, okay, you could see that we got deuteron, right? You just start from hydrogen, you get deuteron. And here, once you have one piece of deuteron, but the initial nucleus you have is hydrogen. You know, the sun is full of hydrogen, okay? The first two hydrogen combine to form deuteron. And the deuteron still there, okay? Still stay there. Deuteron will be combined to another proton or the hydrogen nucleus, and it's going to be, okay, you know, the number of nucleus or a number of nucleons is 1 plus 2, so we get 3 here, and the number of proton by hydrogen and 1 proton by deuteron will be 2 protons, and this is equivalent to helium atom, right? So we get the helium 3 2, okay. it's not alpha particle because the alpha particle would be helium-4 right? But this one is helium-3 We would say helium-3 as the light version of the helium. Okay, this is the light isotope of helium. It's not helium-4. Okay, helium-4 is very, very stable. Okay, and yeah, now from equation 97, we are gonna find the mass difference and multiply it with 931.5. Okay, because we want to convert the mass difference to the reaction energy or the fusion reaction energy. Okay, yes, we start from the mass of the proton. Mass of proton 1.007825 here. Okay, 1.007825. Our next term is the mass of the deuteron. Okay, the bigger hydrogen nucleus. 1 neutron is added. It's 2.014, 2.014, 101 atomic mass unit. Okay, that's the second particle. At the output, it should be negative, right? The output helium-3 Helium-3 is this one, okay, 3.016, 029. Okay, you get this summation and subtraction, and you multiply it with 931. Okay, according to the Albert-Einstein relation, we're gonna convert the mass to the to the energy, right? EMC square. But this is the simple version. We multiply it with 931, we get 5.49 mega electron volt. Okay, yeah, you start from hydrogen and hydrogen, you get deuteron. You start from hydrogen and the obtained deuteron, you get helium-3 In the last process, there are two ways. Okay, there are two ways in the third process. Okay, the first one is that the proton, okay, the proton H11 and the light nucleus combine to form ordinary helium-4 and the positron and gamma. Okay, again, at the moment you get deuteron, you get helium-3. Okay, the nucleus is bigger and bigger. And once you combine it with hydrogen, it's going to be helium-4, right? We don't pick up proton here. Proton turns to be positron. Okay, beta 01. And now we compute the reaction energy, which is the mass of this one. Okay, mass of proton. Okay, mass proton is provided here 1.007825. Okay, this one 1.007825. That's the mass of proton. Now it's plus the mass of helium-3, the light helium. Helium-3 would have atomic mass 3.01, 6029. Okay, 6029, this one. And the outcome is the alpha particle, right, or the helium-4. So we need to go to helium-4, which is 0.00263. Okay, that's the mass of the helium-4, the typical helium version. And next one is the mass of the positron. Mass of positron will be equal to the mass of electron, right? So yeah, we get the mass of electron right here. And after that, we make subtraction and summation. We multiply by 931. We get 19.284 mega electron volt. Okay, 19.284 mega electron volt. That's the mass from the first possible process in the third process. Let's consider an alternative process in the third, in the last process of the sun. This is what the physicists predict. Okay, I'm not sure how they could validate this result. Okay, in the second process for the third process, we don't take proton into account anymore. we just assume that the helium-32, which is the light helium, has exists also somewhere there. So we're gonna add only helium-32 to become helium-42 and 2 pieces of proton or hydrogen nucleus. And based on 101, we could again compute the reaction energy, okay, 2 times of the mass of the helium-32 minus or subtracted by the mass of helium-42 and the mass of 2 times mass of proton. Okay, you just take the value from the table, leave it right here. Okay, mass of helium-32 is 3.016029 and mass of helium-42, right, is going to be there. You just pick up 4.002603. Okay, that's the mass of helium-42, and the mass of hydrogen, okay, which is this one, 1.007825. After that, you make summation, subtraction, blah blah blah, and you multiply it with 931.5. You get the amount of energy from the second process in the third process of the sun. Okay. The above 3 sequential process is known as proton-proton cycle, which is believed to be the status of the energy liberation in the sun and other stars that is full of, that contains a lot of hydrogen atom. Okay, and if it is completely understandable, let's take a look at this figure. Okay, you start from proton, and you get deuteron, right? You get deuteron, and apart from that, we have also positron and electron neutrino, okay, which is a very very small object or a particle, and it has no charge at all. Okay, next one. Once we got helium, deuteron, right? Deuteron will combine with hydrogen to express the gamma or the photon, and now we arrive at helium-32. Okay, that's the left branch. For the right branch, we start in the same way. Okay, hydrogen and hydrogen. It can be called also protium. Okay, some books may say protium, which means proton, but it's in the same sense as hydrogen, so it's called protium or hydrogen 11. Okay, hydrogen 11 combine to each other to get electron neutrino and the positron and electron neutrino, right? In here we have deuteron. Okay, deuteron will be combined with protium or hydrogen 11. We get gamma ray and helium-32, okay, which is the light version of the helium-42. And in order to be stable, they will combine to each other, and they would stay like helium-42. Okay. The light helium will combine to each other, and we get the typical helium-42. Okay, this is helium-32, and apart from that, we get also proton. Okay, 2 protons from this process. It's 3.21. Okay, helium-32 to become proton plus proton or hydrogen 11 nucleus. Okay, as seen from the reactions, the liberated energy is carried primarily by gamma rays. Okay. Oh no. Oh, no. Where is that? Here, right? Okay, the outcome you could see from this figure is electron neutrino, right? And what else? Electron, I don't know, positron, right? This one, positron, electron neutrino. Okay, and what is this? This is gamma ray, right? So the outcome would be gamma rays, gamma, and positron beta plus positron, right? This one, and neutrino, right? Which is the new variable here. The gamma rays will be soon absorbed by the dense gas, and it will raise the temperature of the dense gas. The positron will combine with electron to produce gamma rays, which in turn are also absorbed by gas within few centimeter. Okay, it could not escape so much. Okay, the gas around there will absorb the gamma ray or the photon. And the important thing is the neutrino. Neutrino will never act or interact with other matters, so it carries around 2% of that generated energy to somewhere else. You know, even we live here on Earth, there are many neutrinos from the sun, okay, that are moving to us on Earth. Okay, because the neutrino doesn't act or interact with any matter. The energy liberating fusion reactions are called thermonuclear fusion reactions. So this one, okay, it's increase also the temperature. So the net energy released, could be calculated from the mass balance, and it turns to be 26.7. Okay, if you add everything, it's going to be 26.7. Okay, this one, okay, you get 26.7 mega electron volts from the whole process here. And if the sun were to continue to radiate at present rate, around I don't know, 130,000 kilowatt hour, okay, that's the amount of power energy that the sun deliver. Okay, if there is a burning process that will deliver energy like 130,000 kilowatt hour. Okay, so our Earth, or the time that will let the sun completely disappear, will be 75 billion years. Okay, we still have time for 75 billion years, and the sun will stop working. Okay, to give the nuclei enough kinetic energy. The fundamental challenge of nuclear fusion is that we have to give the nuclei enough kinetic energy. What is the reason behind it? Because the nuclei will fuse to each other once they are very, very close to each other, and in order to bring such tiny particle to be close to each other, we need a lot of energy, and it should be in a very, very high temperature environment, so that there will be very high kinetic energy amount. Okay, yeah, because you know, in nuclei there are some protons, right? And protons are positive charged. Of course, plus or positive charge and positive charge will have Coulomb force. That is the repulsive, right? Pushing force to each other. And yeah, but you need to bring the nuclei to be very, very close to each other, so that they can interact and will build up a new nuclei for you, right? That's the thing we want. And yeah, for two nuclei to fuse, they must come together to within the range of the nuclear force. And you know, the nuclear force in the in the previous chapter, right? Nuclear force is in the range of 2 femtometer. Okay, so you need to leave two nuclei to be close, like 2 femtometer, which is 2 times 10 negative 15. Okay, which is very close to each other. But for us, it's already the same point, right? But it's not the case for the nucleon because they are in a very tiny scale. Okay, at the distance of 2 femtometer, we need to put the potential energy for those two protons. And the energy will be on the order of 1.1 10 to negative 13 joule or 0.7 mega electron volts. Okay, we would get the energy like a 0.7 mega electron volt. It's considerable amount, right? It's not like in June you have 10 to negative 13. It's very hard for human to understand. Okay, the temperature T for a gas with the average translational kinetic energy from the Boltzmann formula will be 3/2 times K. Okay, K is the Boltzmann constant. Okay, maybe you have ever heard it. The Boltzmann constant, and we convert the translational energy to become the potential energy. And the temperature to get this amount of energy, it should be 5 times 10 to 9. So what is that? 5,000 million Kelvin. Okay, you have to build up a laboratory with that could support the temperature of 5,000 million Kelvin. Okay, so that the nucleus will be the nuclei will be close to each other and the nuclear fusion could take place. All right. Yeah, temperature must be on the order of millions of kelvins, as you can see here, 5,000. So that the nuclei are to have enough kinetic energy to surmount the electric repulsion. You know, proton and proton will push each other. Okay, and you need to have you need to have sufficient amount of energy, of kinetic energy, and in order to do that, you need to be in the environment of 5,000 Kelvin, very hot. Okay. Fusion reactions that appear most promising involve the deuterium-2 and the tritium. Okay, this is the expected fusion reaction process that human would like to use for like producing, for making the electricity and so on, or any other kind of energy consumption. Okay, you just start from 2 pieces of deuterium. Okay, and of course, you know, 4 nucleon, 2 proton, right? And this one is helium-32. Okay, and this one is neutron, right? So let's compute the energy reaction, the reaction energy from this process, right? It's in the same way. You have to find the mass difference. The left hand side is positive, the right hand side or the output will be negative, right? So this is the mass of the deuteron. Okay, let's go to the atomic mass table. Atomic mass table. Okay, here. Atomic mass table. Here is deuteron, right? Deuteron has a mass, atomic mass is 2.014101, yes, times 2. And minus helium-32 minus helium-32. So helium-32 means 3.016029. Okay, this one, helium-32. And mass of neutron is over there, prepared already here. 1.0086, okay, almost the same. And you just find the subtraction, and you get, and you have here 9314.5 for multiplication, and finally you get 3.2677 mega electron volts. Okay, and another kind of process starting from deuterium is the following. Instead of helium-32, the two deuteron may provide tritium. Okay, tritium is a bigger isotope of hydrogen than the hydrogen 1 or the proton or the deuterium. Tritium is bigger than deuterium, but they don't provide the atomic mass of tritium here. Okay, and of course, apart from tritium, we're gonna have proton or hydrogen nucleus right there. Mass of deuteron is here 2 times 2.014101, and mass of tritium, right? Tritium is the bigger isotope of hydrogen. Okay, and the next one is the mass of hydrogen. Okay, we take this value 1.007825. Okay, we make the subtraction and we get multiplication. We end up with 4.0315 mega electron volts. Okay, that's the process starting from 2 pieces of deuteron. And the last one is the process between deuteron and tritium. Okay, bigger and bigger nucleus. Okay, yes, you start from deuteron D21 and tritium 31, right? We end up with helium-42, okay, the stable nucleus or the alpha particle. And according to the balancing equation, we have 1 nucleon remaining here, and that's the neutron. Okay, it's not, there is no proton at all. So this is the neutron. And after that, we make the computation of the mass difference, mass of the deuteron right here, mass of the deuterium, sorry, here 2.014101. Okay, and mass of tritium is not available here. You need to go somewhere and pick up the mass of tritium. Okay, mass of tritium. Next one is the mass of helium-42. Helium-42 is over there, 4.002603. Okay, it's not difficult. And mass of neutron is also here, 1.00866. Okay, blah blah blah. After that, you make the summation and subtraction. You get you have to multiply at the end with 931.5. You get 17.589 mega electron volt. Okay, it's much bigger than this process. Okay, and even this process. The lightest one will be 3.27 mega electron volt. And once your element is bigger, okay, you may get like 4.0315. Okay, from deuterium and deuterium. But for deuterium and tritium, you may get the energy on the order of 17, blah blah blah, 17.589. Okay, let's consider another kind of fusion process. Okay, it's not a series process, but it's quite important. This is taken from example 30.2 from the book number 1. Okay, and then we are gonna start the particle physics soon. Okay, in this one, nuclear fusion, right? Determine the energy released in the reaction of a helium-3 with a deuteron according to this equation. Helium-3 plus deuteron. Okay. Before that, we have deuterium and tritium, right? We end up with normal helium-4 and neutron. For this one, we start from helium-3, the light version of nucleus, and the deuterium, the deuterium, and we end up with helium-4, the alpha particle, and 1 proton. Okay, so what is the energy released in this reaction? And we need to have it in mega electron volt, right? The way to compute is the mass difference between the input side and the output side, and once you get the mass difference, you just multiply it with 931.5, so you will get the released energy, right? Okay, helium-3 is the first reactant, right? The initial chemical agent, the initial agent. Next one is the deuterium, MD21, right? Next one is helium-4 and proton 11, or helium-11. Helium-3 has the mass, in the following table. What is that? Helium-3, right? Helium-3, this one, 3.016029. Okay, just take this value and leave it here, right? Next one is deuterium. So the mass of deuterium has to be later, plus mass of deuterium. Deuterium has the mass of 2.014101. Okay, 2.014101. It's positive on the left hand side, and on the right hand side is negative, right? Helium-4 minus mass of helium-4. Helium-4 here, 4.002603. Okay, this one. And mass of proton, 1.007825. Okay, that's the mass of the proton. And you make subtraction, deduction, and you multiply it with 931.5. Okay, 931.5. You will get the reaction energy or release energy as 18.352. Okay, 18.352. Okay, if you compare it to deuteron and tritium, yeah, the bigger and the bigger nuclei that combine together, the more you will get the energy from that process, from fusion process. Okay, this 17 and 18 right here. Okay, so the bigger the nuclei you are involved, the more the power you could get from the process, and that's the whole thing about this. All right. Next, we go to the particle physics, which is the last section of this chapter. Okay, but the lecture notes are not completely prepared. Okay, we are gonna we will do it later. Okay, let's consider this. Okay, the second section of this chapter is particle physics. Okay, actually, you have seen already the standard model of elementary particles in physics, right? That has boson, leptons, right? In quarks and so on, right? Okay, before we go to the detail of several particles in physics, you need to know the type of the forces that exist in physics, right? There are four kinds of forces in physics, right? All particles in nature are subject to four fundamental forces, which are the strong force, electromagnetic force, weak force, and gravitational force. Okay, there are four forces in physics. Okay, and the strong force is responsible for, okay, this, let's consider the first type of the force. It is the strong force. Okay, strong force is somehow like nuclear force that you have seen at the beginning of this chapter. The force that try to combine several nucleons to stay together as a nucleus. Like you want to combine proton and neutrons, right, together to get the nucleus of some elements, right? And yeah, strong force is responsible for tight binding quarks, okay, to form neutrons and protons, and okay, this one is called gluon actually, and the nuclear force, right? The nuclear force that binds the neutrons and proton to form a nucleus. Okay, this force represent the glue that holds the nucleons together and is the strongest force of all the four fundamental forces. Okay, and the strong force, as is the name suggests, it is the strongest one. Okay, of the four forces: strong force, electromagnetic, weak force, and gravitational force. The problem is that it is a very short range force. Okay, it's not very far. It's on the order of femtometer 10 to negative 5. Oh, sorry, negative 15 meter, not 5. Okay, the number 1 is missing here. I'm sorry for that. ต้องมีเลข5ครับ 15. Okay, 15, not 15, not 5. It's going to be changed later. Okay, that's the bad thing from the strong force, because it is short range force on the order of femtometer. And the next one is electromagnetic force. This is what you may have seen, right? It is about 1 by 100 times strength of the. It's 100 times weaker than the strongest force. Okay, it may not be so strong as the strong force, and the functionality of the electromagnetic force is to bind the atoms and molecules together, right? They have positive charge, negative charge, and so on. That belongs to electromagnetic force. All right. It's a long-range force that decreases in strength as the inverse square of the separation between interacting particles. So the range of interaction is bigger than the strong force, but the strength of the force reduces with the square of the separation or the distance. Okay. So the time is over. Right now we are gonna finish our lecture for today. If you didn't write down your name, just write down in any YouTube channel, up to you. And we don't see each other on this Friday, right? So see you next Wednesday for M605. โอเคครับก็วันนี้ก็จบเพียงเท่านี้นะครับไม่มีการบ้านนะครับพบกันพุธหน้านะครับif you have any ถ้ามีคำถามนะครับโปรดถาม if you have any question just let me know if not then bye bye ครับสวัสดีครับ